Okay, we go to a new chapter, equilibrium of a rigid body, conditions, conditions for rigid body equilibrium. Okay, so as you already know that what is a rigid body? A rigid body is a body which cannot undergo deformations or deflections on the application of force regardless of the magnitude of the force that is acting on the rigid body. So in chapter 3 and chapter 4 we have done how to basically resolve and basically various forces. In chapter 4 we have basically understood the concept of movements, the concept of couples, the concept of couple movements, and also the how loading is being applied on various systems. This we already know. So now here basically we in this chapter we will be having systems on which there will be forces acting on a system and there will be movements acting on a system combined in a combined way. So we have to solve those forces and both the systems to get basically the effect of the forces and movements on those systems. So here you can see basically there is a crane and then there is a hook and which is a boat is being applied, and then basically because of the weight of the boat is acting downwards, and these four components tension is being acting upwards, and then basically this crane is being supported by beams horizontal uh, hydraulic pistons over here you can see. So we'll be very much interested in basically what is the force is generated on the supports of these pistons, and what is the tension generated over here in these ropes or wires. Another example, if you look at it over here, is you can see a beam. These beams are being basically being used in bridges on which cars and trains can move about. The transportation takes place. So if this beam is to be transported by means of wires and ropes, then you can see there are two blue arrows on the upside in plus y direction, and then there is the resultant weight of the beam which is acting downwards. So the beam is basically in equilibrium under the action of its own weight and the forces exerted by the chains or ropes. Okay? So this beam we assume it is in equilibrium because of its weights, and then there will be some forces exerted on the chains. Why it is being exerted on the chains? Because of the weight of the beam. And so in this chapter we apply the equilibrium equations to determine the unknown couples acting on the object. So now here we can read that when an object is acted upon by system of forces and movement is in equilibrium, we have the following conditions. And you already know that the sum of the forces acting on the system will be zero, summation of all, and the sum of the movements about any point is also zero. Sigma f equals to 0, sigma m equals to 0. Okay. So to provide insight into the nature of equilibrium from the standpoint of total forces and movement exerted in equilibrium, the effects of the same if no force or couple acted on the object. So this is a very important observation. It will make it clear that if the sum of the forces on an object is zero and the sum of the movements about any point is zero, then the sum of the movements about every point is 0. Okay, so this is what it's trying to say, that if we say on a body that we only say that the summation of forces acting on a body is 0, and we do not use that and tell movements equals to 0, then the body may be in equilibrium, it may not be in equilibrium. But if the movements are also on acting on a body is 0 and forces acting on a body is 0, then we can be very safely saying that the body is in equilibrium. Okay. So when the loads and reactions on an object in equilibrium forms a two-dimensional system of forces and movements, they then uh, three scalar equilibrium equations are developed, and which I told you for in our previous numericals also you have got basically three equations to solve. They are sigma fx equals to 0, sigma fy equals to 0, and you can take movement at any point of your interest to write sigma m summation of all the movements at any point equals to 0. Okay, so this is these equations plays a very important role. Then again, very important information about supports. What are supports? So I told you supports in our previous numericals. You see whenever a bridge is there, a beam is being placed, then one side has pin, other has got roller. These are supports. Okay, so when you are standing, the floor supports you. This is a very good example. When you sit in the chair with your feet on the floor, the chair and the floor supports us. Okay, it's very important and very simple. They are supporting us. If they are not there, we will fall down. We will fall down, we will go underground, things like this. So we are concerned with the ways of an object can be supported or held in place. Forces and couple exerted on an object by its supports are called reactions. So this is very important, that they say the forces and the couples which are exerted on an object by its supports are called reactions, expressing the fact that the supports reactions to the other forces are couples or loads acting on the object. Okay, so you have also understood a very important terminology, reaction and supports. Okay, whenever a force is being acting on supports, the support will generate reactions as a result of those forces. You must remember this point, very important. Okay, so the support basically reacts to the other forces, and not only those reactions can be generated as a result of force, but they could also be generated as a result of couples or loads acting on the object. So a bridge is held by the reactions exerted by its supports and the loads and the forces exerted by the weight of the bridge itself. So the traffic crossing it and the wind. Some very common kinds of supports are represented by stylized modes called support conventions. Okay, actual supports often closely resembles the support. Okay, if you look at this example, what do you see over here? Okay, you see in the figure a bracket is being there placed. You can see here a bracket is there, then there is a beam or supported object, and then there is a pin. This pin is supporting not only the bracket and also the supported object. If this pin is removed, the relation between the bracket and the supported object will not exist. Okay, so A is a pin support. B, you can see side view showing the pin passing through the beam. Okay, so you can see this is the beam, and these are two pins. You can see one side, the other side will also be there. Okay, so C is the holding the support. If you hold it, if you are trying to hang your weight or something like this, so it is a holding support bar. And what is D? It is the pin support that is capable of exerting two component of forces. Okay, so you have already understood this is a pin support. Okay, so this is the most important support we will see. This figure shows you pin support. The diagram represents a bracket to which an object is attached by smooth pins. The reactions that these pin supports can exert is helpful in holding the bar attached to the pin support. So what is he saying is that over here, if there is no pin, then this bar will not be supported. This is he's trying to say. So if you try to move the bar without rotating, it translates the bar. That support, the support exerts a reactive forces that prevents the movement. However, you can rotate the bar about the axis of the pin. The support cannot exert a couple about the pin axis to prevent the rotation, and that's thus a pin support can't exert a couple about the pin axis. What is he trying to say over here is that if you look at this pin and you can look at this pin, if I try to move with my hand along the x-axis to move this bar along axis, can I move it? No. But if I along my bar, I take it vertically, put the beam like this in a vertical direction and try to move in the y-axis, can I do it? No. So what is he trying to say in this theory here is that he's trying to say that the pin will provide me reactions along x and y, and those reactions will be termed ax and ay. Okay, and then but on the contrary, if I try to with my hand rotate this bar in 180 degree or 360 180 degree pattern, say 180 from here to here in an anti-clockwise direction, it will be easily rotated. So he is trying to say that the pin will not provide resistance against the couple movement, but it will provide the resistance along the x and y axis, ax and ay. That is, we are trying to say the arrows indicates the direction of the reactions if ax and ay are positive. If you determine ax and ay to negative, the reactions in the direction opposite to that of the arrow. So these reactions ax and y, if you calculate, this will be your main aim to calculate these reactions ax and ay, and you will always assume that you can assume, it is up to you, that ax ay will always be positive. But when you solve your calculations and the result comes out to be, say, ax or ay are both negative or any one of them negative, it means that the direction that you assumed was wrong. So you can assume a wrong direction, that's perfectly fine. So it's but a general uh, basically what is called as methodology is basically is there that convention rather is that the AXAY components will always be assumed positive. It's a convention, you can take negative also. Okay, then he says that the pin support is used to represent any real support capable of exerting a force in any direction but not exerting a couple. So pin supports are used in many common devices, particularly those designed to allow connected parts to rotate relatively each other. Now, very common example at your home, where any basically you are using a stapler, and you can see when just you can, if you have a stapler, you can see this small location joint at which there is small pin-like structure attached on one side and the other. What you can do is that this stapler can easily rotate. You fix your hand here and you can move it like this. Same with the scissor. If you look at this scissor can be opened and closed with your hand by the rotation of this pin. Okay. The roller support, again after the pin support, and you already learned that the pin support will give you two reactions. Then comes the roller support. The convention called a roller support, again roller support, if you look at from your metric classes and college, you know about the roller support. If whenever a bridge is there, one side is pin connected, other is roller. For the expansion and contraction during the summer and winter, you put a roller support. Okay. Remember, just go in your past and you will remember this, your teachers saying that, the school and college teachers. So the conventional roller support represents a pin support which is mounted on wheels. Again, that is what I am trying to say. Whenever a pin support is there, it will be mounted on small wheel-like structures. It can be metallic wheels also. Okay, it can move freely. It can move freely in the direction parallel to the surface on which it rolls. It means if we put rollers over here, okay, then what it will happen that it can translate along x and y if a roller is here. What is he trying to say? The same thing over here. The wheels of the vehicles and wheel supporting parts of machines are roller supports. This is very example saying the wheels of the vehicles and wheel supporting parts of machines are roller supports. Then bearing also has got a roller support. If the friction force is exerted on negligible and compared to normal forces, a plain smooth surface can also be modeled by a roller. Okay, so this is a very good example. We will see what is basically a roller support now. Okay. Okay. So now we go to roller support. If you look at it, this is your bar or your beam, and this is your again your roller support. But you look one thing common between the pin and the roller, that this roller is being connected to the supported object bar or beam by means of a pin. And if you look at it, these rollers have the capability to move along the surface, to displace, not move but rather displace very small displacements is affordable by virtue of these two wheels. These wheels can be metallic, plastic, depending upon the load it can support. But if you look at this roller over here, this roller cannot move in a vertical y-axis direction. If you want even with your hand to move it, because it will be fixed in the ground, this roller will be fixed with the capability to move along the say x-axis. So this roller will give you a reaction A. This is the reaction. It cannot be moved above the y-axis. Even though if you try, the reaction will be generated A. This is the roller's support A. B, the reaction, what I told you, the reaction consists of a force normal to the surface, and what is C, it supports the equivalent to the roller support. Now over here you can also have other supports also which could be treated as a equivalent to the roller support. Why they say equivalent? The question rises now. So for equivalent, what do they mean is that this roller is giving us one reaction. So we can put it like this, or is also a roller. This is a roller, one big roller. It is an equal support. This is a roller support, this is a roller. This is the difference. Then there is an I section beam on which the support is placed, or there is a rocker also. This is called as a rocker. Remember, it will also give you one reaction like A. It will also give you one reaction like A, and if you look, it will also give you a one reaction. So these are called as equivalent to the roller support. Okay. So just to read that what is saying, beams and bridges are sometimes supported in this way so that they will be free to undergo thermal expansion and contraction. Just I told you before, they are trying to tell you the same thing. So they are similar to roller supports in that they cannot exert a couple and can only supports. Here basically they are trying to say, and the supports here also in figure 5.5, they are similar to roller supports in that they cannot exert a couple and can only exert a force normal to the particular direction. This is a pin in a slot. Slider, this is a slider in a slot. These are again supports, very unique type of supports. Slider on a shaft. This is a shaft on which a slider is being placed. Okay. So the supports object is attached to a pin or a slider that can move freely in one. Slider means it can move freely in one direction or the opposite direction, but it is constrained in the perpendicular direction. See here, it cannot move in vertical. This cannot move in vertical direction. Okay, so unlike the roller support, these supports can exert a normal force in either direction. Okay. So now we go to the fixed support. This is the most important support and the most unique support that we will encounter. Okay. So you must, and it will be very helpful. It will make your life very easy when solving numericals. It's a very friendly support. Okay. The fixed support shows the supported object literally built into the wall. Okay, if you look at it, this here what he is trying to say, this is a wooden bar or any metallic bar being fixed into the wall. Okay, he is trying to say. So this convention is also called as built-in support. We will call it as built-in support also. To understand the reactions, imagine holding a bar attached to a fixed support. So again, to understand reaction, you will support a bar which is being attached to a fixed support here. And if you try to put your hand and try to bend it downwards, so where will be the reactions generated? It will generate it somewhere here. Okay. So what will be the nature of the reaction? This picture shows you because of any force, this will be the reactions. Okay. So A is the fixed support. If I say this is the A point, this is overall called as the fixed support. Holding a support bar. B, it is holding a support bar, and C, it is trying to tell you these are the reactions. Again, this here is basically in C is the, this is A, this is B. Okay, just to let you know, this is A, this is B, and this is C. Okay, the reactions at a fixed support is capable of exerting. So what type of reaction we see here? It is a horizontal reaction AX, then a vertical reaction AY, and then there is this movement MA. Now your job is, if a fixed support comes in a two-dimensional structure, remember it will have always these three reactions. Your job whenever this happens is basically to calculate AX, to calculate AY, and then to calculate MA. This will be your assigned task. What he is trying to say here is basically there are two force components and a couple is being placed. These are the AY and AX are called four components, and this couple is MA. Okay, they are being generated. Okay, here. So these are the supports which are used in two-dimensional application. Just to let you know, if you have got a rope or cable over here like attached, or you've got a spring force. So this, if a numerical comes, it will be showing you a figure like this. So if a numerical comes, it will be showing you a figure like this, and a spring is placed in that numerical, and this in the structure. You need to replace it with this tension T. Okay. So it will be a collinear force. If you have got a contact with a smooth surface, and they will tell you show this figure and say it is a contact with a smooth surface. So because of the smooth surface, a force normal to the supporting surface is generated. So you will replace this in the FVD with this one reaction. So if you have got a contact with a rough surface, if the contact is there with a rough surface, you will always have two force components, AX and AY. If they say the surface is rough, it will have two force components. If it is a smooth surface, it will be a one force normal to the supporting surface. This already you know. If you have got a pin support, if you got a pin support, then your force components will be AX and AY. Okay. And again, this you have done it before, and if you got a roller support, if you got one big roller, an I section or a rocker equivalent to all those rollers, then there will be a force normal to the supporting surface is generated. This will be a force which is normal to the supporting surface is generated. Then you already know that we have studied before that if you got a constraint pin or slider over here, this is a slider, constraint pins, again it will be a normal force. Fixed support is there is two force components and one couple. If you have got a rocker support, if you say this is a rocker support, this will be a force reaction. So it will say that there will be one unknown. The reaction is a force which acts perpendicular to the surface at a point of contact. If you have got a smooth contacting surface, it will be also have the one unknown, and the reaction is a force which acts perpendicular to the surface at the point of the contact. Okay, so they will tell you in the numerical that it is a rocker. Okay, so and they will tell you smooth contacting surfaces. If you've got member pin connected to the collar of the smooth rod, over here the direction can be like in this sense direction, or direction can be in this direction. So it will be one unknown, and the reaction is a force which acts basically perpendicular to the rod. Okay, and again if you got a cable installed over here, again these are examples of just to let you know from I'm telling you about two different books, Hibbeler also and one reference books also. They are showing you pictures. These are I think the pictures of the Hibbeler. Okay, so yeah, cable is there. You already know one unknown. The direction is a tension which acts away from the member, the direction of the cable. If you have another support or weightless link is here, then it will be again one unknown. Direction of the force acts around the axis of the link. If you have got roller here, if the roller pins here, okay. Then comes another RC Hibbeler supports, which is tell you smooth pin hinge. You already know that whenever a pin is being there, it will give you two reactions, Fx and Fy, and this Fx Fy can have a resultant also, F at an angle theta. Here theta will be for the resultant force, not for the beam or the bar. So it tells you that there are two unknowns. The reactions are two components of the force or the magnitude and direction phi of the resultant force. So here is phi is the angle of the force and theta is the angle of the bar or the beam, and they can be equal, they cannot be equal unless the rod shown in link is in 2. Member fixed connected to collar or smooth rod. Here it is. If this support comes, then you will have one force reaction and there is a couple movement. Okay, it can rotate. Two unknowns reactions are the couple movements and the forces which acts perpendicular to the rod. And this is the fixed support, again telling you. You have the fixed support, you will have two force components Fx Fy, and one is the couple movement. This Fx Fy, just like the pin, can give you a resultant Fr. This is FRRF, and one is the movement. This can further be resolved as Fx Fy, which is the same as this one. So it tells you there are going to be three unknowns, and the reactions are the couple movements and the two force components are the couple movements and the magnitude and direction phi of the resultant force. Okay, so this is from another book. Just to let you, there are more like rope or cable to show you clearly. This and the other and the RC Hibler are exactly the same. Just to let you know for further examples, like they're telling you contacting with a rough surface, a new support over here is placed. Okay, so they're exactly one and the same. You can learn from anyone here also or other. The output is the same. This is from RC Hibler, and this is also from the RC Hibler. Okay, just to let you. Okay, let's see this picture of the beam. This is a beam. It has two supports, and if you look at the supports, the left support is a pin support and the right support is a roller support. You can see two wheels on roller at point P. But this roller, if you look at it, is not along the ground, along the like the pin. It is inclined at 30 degrees with the x-axis. So now the normal reaction will be perpendicular to the surface, not the ground. So if you look at it here, is that this is your pin, this is your roller, and this is the force acting. So this is pin, this is roller. So if you look, go back, if you go back, again we go back. Here is a roller, here is a roller, okay. So this roller gives you one reaction. It is inclined at an angle theta, just like in the picture that we were discussing. So the reaction is perpendicular to the surface. And if you look, this is the pin. This pin will give you two reactions, Fx and Fy, as from this table. So if you draw the free body diagram, which is very important, this pin gives you two reactions, Ax and Ay. This is the force acting. The roller gives you one reaction, and this angle is 30, so this vertically y also this angle is 30. So reactions due to the pin support and reactions due to the roller support. So a beam with pin and roller supports, and B, isolating the beam from its support, and C is basically trying to tell, here it is isolating the beam from its supports, and this is the completed free body diagram. Ax, Ay, this. So just what I told you, explain this thing with here also understood as that the pin support at the left end of the roller support at the right end of the loaded by a force F. The roller support rests on a surface inclined at angle 30. Here it is trying to tell you This roller support is resting at an angle to surface at 30. The free body diagram of the beam is shown here. So what is it trying to say, that we can complete the free body diagram by showing the reactions that will be exerted on the beam. Again, this free body diagram can be completed by drawing the reactions of the pin supports and the roller supports. Okay. So the object, if we go further away, in 5-8, you have an object fixed here with a cable being attached and a pulley being attached over here. It is being fixed, and this pulley is basically attached to a spring here also and here also. Okay. A, an object with a fixed support. B, isolating the object, can isolate the object from here. And C, completed free body diagram. So what is it trying to say here? So the object has a fixed support from to the left hand. A cable passing over the pulley is attached to the object or at two points. So we isolate it from the support and complete the free body diagram by showing the reactions at the fixed support and the force exerted by the cable. Okay. So you forget the couple at a fixed point. Don't forget the couple at a fixed support. Since we assume, because we know why is in couple, because the fixed support will have two force components and one couple moment. Since we assume the tension in the cable is the same on both sides of the pulley, so this again, this is an example. It can be different also, but we will always assume, for our numerical to be easy, we will assume the tension in the cable is the same on the both sides of the pulley. So the two force exerted by the cable have the same magnitude T. Okay, so once you have obtained the free body diagram of the object in equilibrium, to identify the loads and the reactions acting, you can apply equilibrium equations. Okay, so this is the tension T, this is the tension T as a result of the cable, and this, it is fixed. So we can say AX, AY, and this couple movement MA. This is a built-in support.